So for this topic, we will be looking at how to calculate internal forces that are generated because of loading. The internal forces that exist in beams are shear force and bending moment. We will learn how to calculate them and plot them graphically. These graphs are called as shear force diagrams and bending moment diagrams. They can also be shortened as SFD and BMD, wherein SFD is shear force diagram and BMD is bending moment diagram. First, let us look at what happens when a beam is loaded. When a beam is loaded, it will deform. That is, it will bend in the direction of the load. When this bending occurs, the beam will experience internal forces. Two internal forces which a beam will experience at this point would be shear force and bending moment. For shear force, let us assume that we have a beam which is supported on two ends by supports. The support reactions are depicted. We can visualize this scene in this right side diagram. So there is a beam and then it is supported in both the ends. The support reactions are depicted using R1 and R2. Two loads W1 and W2 are also acting on this beam. These loads are gravity loads or downward loads. Shear force is the force acting in a direction parallel to the cross section of the beam. Thus, shear force will act either downwards or upwards across the cross section of the beam. Shear force is the sum of all vertical forces on one side of a section. Let us assume that we have a section x dash across the beam. Shear force is the sum of all vertical forces on either side of this section. The sign convention for shear force will depend on the direction of the force and the side of the section. This figure gives us the sign convention for shear force on the left side and the right side of the beam. Downward forces or gravity load on the left side of the beam are negative, while positive or upward reactionary forces are positive. Similarly, upward reactionary forces on the right side of the beam are negative, while downward gravity loads are positive. Thus, if we were to calculate the reactionary forces or the shear force for the left side of the beam, we can calculate it to be minus W1 because it is downward force on the left side plus R1 because it is a positive force on the left side. Thus, the shear force for the left side of the beam is minus W1 plus R1. Similarly, on the right side of the beam, the gravity force is positive and the reactionary force is negative as we discussed earlier. So, here the equation will be W2, which is positive W2 plus W2 minus R2. Generally, shear force is depicted using Newton or kilonewton as its unit. Now, let us look at what a moment is. Moment of a force is a measure of its tendency to cause a body to rotate about a specific point or axis. Let us assume that we have a section. This section is a beam, or let us assume that it's a cantilever beam. The cantilever beam is as given in the diagram. When a load acts at the end of this point, this cantilever beam will tend to rotate along a fixed point which is given in the second diagram. Now this is called a moment. Moment will develop when the force causes the body to twist. Moments are formed when force does not pass through the center of gravity of the body. If the force was acting along the line, this body would not rotate and does not have a moment. However, as this force causes this portion of the beam to rotate, it causes a moment. This is different from translation motion or movement in the direction of the force. Next, we look at bending moment. Bending moment is the tendency of a force to rotate about a point, or it is the turning effect that is produced by the force. Bending moment is thus calculated to be force into the distance from the location of the moment. Let us assume that we have a beam that is supported on two sides by the reactions R1 and R2. Thus, reaction forces R1 and R2 act upwards. We also have a downward gravity load W. This gravity load W is acting on the span of the beam. Now, the span of the beam is L. Now, let us assume that there is a section x dash across the cross section of the beam. This section is at a distance D from R1 and a distance L minus D from R2. Let us also assume that W1 acts at a distance x from x dash. Let us also assume that W1 acts at a distance x from x dash. Now, when we look at the sign convention for bending moment, a downward load produces a positive bending moment and an upward load produces a negative bending moment. The sign of the moment is opposite to the direction of the bending moment that causes downward bending or sagging, and negative moment causes upward bending or hogging. Any load that tends to cause sagging in the beam will be considered to have positive bending moment, while any load that causes hogging in the beam will cause negative bending moment. Thus, if we were to calculate the bending moment at section XX for the left side of the beam, we would calculate R1, which causes sagging to be positive. So, which means that R1 into D, while W1 causes hogging. Thus, it is a negative moment. Thus, the net moment at section X dash is R1 into D minus W1 into X. Similarly, if we were to calculate moment on the right side, it would be R2, which causes sagging again, thus positive. So, R2 into L minus D, which is the distance from the section XX. Now, let us look at shear force and bending moment diagrams. Shear force and bending moment are internal forces on the beam. These internal forces act over the entire length of the beam. They can be graphically represented also. These graphical representations are called as shear force diagrams SFD and bending moment diagrams BMD. Let us assume that we have a beam with loads acting on it and a section XX which is given. We can calculate shear force and bending moment at each point across the span of this beam and plot it. This will give us the variation of shear force and bending moment across the length of the beam. This will help us see how the entire beam will respond to it. So, to calculate these, we will see an example. So, from this example, let us see how to calculate shear force and bending moments in beams. Let us take a simply supported beam. The beam is supported at two ends on two simple supports 1 and 2. The beam is loaded with a concentrated point load W1 and a uniformly distributed load W2. The span of the beam is L. The value of W1 is 10 kilonewton and the value of W2 is 1 kilonewton per meter. The 10 kilonewton load acts at 3 meters from the support, while the 1 kilonewton per meter a uniformly distributed load acts over a length of 4 meters from R2. The span of the beam is 10 meters. Knowing these values, we have to calculate R1 and R2, which are the support reactions. Now, to see how it is done, we will assume that the beam system is at equilibrium. This means that the net shear force inside the beam and net bending moment inside the beam are equal to 0. Knowing this, we can now calculate the reactions and moments within this beam. And the first step is to resolve the uniformly distributed load into a point. This is done by multiplying the intensity of the load, which is 1 kilonewton per meter, by span over which the load acts, which is 4 meters. 1 kilonewton per meter multiplied by 4 meters gives us 4 kilonewton. This 4 kilonewton concentrated load will now act at the center of gravity of this load system, which is at 2 meters. Thus, the concentrated point load of 4 kilonewton acts at 2 meters from R2. Knowing this, we will assume that the net shear force within the system is equal to 0. This means that the upward loads are equal to the sum of the downward loads. Thus, R1 plus R2, which are both upward loads, will be equal to 10 plus 4 kilonewton, which are the downward acting loads. So, from that, we can also tell that R1 is equal to 14 minus R2. Our next step is assuming that the net bending moment within the system is also equal to 0. This means that the bending moment at any point on this beam is equal to 0. Let us assume that moment at R1 is equal to 0. Knowing this, we can plot the following equation. R2 into 10. R2 is the reaction force at the second support into 10, which is the distance at which R2 acts from R1, is equal to the forces on opposite sides or forces that are acting downwards. And for this we can say that 10 into 3 plus 4 into 8. So therefore from this calculation R2 will be equal to 6.2. So finally, to get R1, we can simplify this equation. We can simplify this value in the first equation where we found that R1 is equal to 14 minus R2. And finally, we'll get the answer R1 is equal to 7.8. So R1 will be equal to 7.8 kilonewtons. Thus, we now know the values for both R1 and R2. Let us now plot the shear force diagram for the simply supported beam. Shear force units are in kilonewton. The shear force at R1 is equal to 7.8 kilonewton. This is depicted by the upward positive line. The shear force does not change as long as there is no change in force across the beam. Thus, the shear force remains constant until the next change in force occurs. This occurs at W1, which is 10 kilonewton acting downwards, or it can also be called as a negative force. Thus, the next shear force at W1 is equal to 7.8 minus the negative 10 load, which is 10 kilonewton, which gives us negative 2.2 kilonewton. Again, shear force remains constant as long as there is no change in the load. As soon as we reach W2 or the uniformly distributed load, the shear force will now reduce uniformly. Over this 4 meter span, the shear force will reduce at an intensity of 1 kilonewton per meter. Thus, the net reduction in shear force is equal to 4 into 1 kilonewton per meter. This gives us negative 4 kilonewton change. Thus, the next net force at the end of the uniformly distributed load is equal to minus 2.2 minus 1 into 4, which is equal to 6.2 kilonewton load. Again, in this area we have a positive 6.2 kilonewton load acting at R2. This is depicted by the second red line. Thus, this figure gives us the variation in the force across the beam. The positive portion of the shear force diagram are given in blue color, or you can say violet, and the negative portion is given in orange color. So with this we can find the distinct difference between the negative and positive portion. Our next step is to plot the bending moment diagram for this simply supported beam. The net bending moment at the ends of a simply supported beam are equal to 0. We know this as the simply supported system has only one vertical reactionary force, while the horizontal reactionary force and bending moment are equal to 0. This is what we saw earlier. So with this we know that M1 and M2, which are the bending moments at the reaction supports, are 0. Our next step is to calculate the bending moment at W1, or where we have 10 kilonewton load. We can calculate the net bending moment on either side of this section. Thus, for sake of simplicity, we will take the left section of the beam. The left section of the beam as in all the loads that are acting at the left section at W. Thus, MW1 or the moment at W1 is equal to 7.8 into 3. So, MW1 will be equal to 23.4. So, basically the net bending moment at W1 is equal to 23.4 kilonewton. Similarly, we will now calculate the net bending moment at W2 or the starting point of the uniformly distributed load. Similarly, we will again take all the loads that are acting on the left section of the beam. Thus, MW2 will be equal to 7.8 into 6 minus 10 into 3. So, our net bending moment at W2 will be MW2, which is equal to 16.8 kilonewton. If we connect all these points, we will get the bending moment diagram for the simply supported beam. Since this entire section is positive, we will be depicting the bending moment diagram using the violet color. Now, by combining the shear force and bending moment diagrams and placing them in the same graph, we can see the simply supported beam with all the loads and distances and other variables marked here. We have the shear force diagram showing the maximum and minimum shear forces all in kilonewton. Then we have the bending moment diagram, which is all shown in kilonewton meter. Shear force and bending moment diagrams are important in structural analysis because they give us the points of maximum shear stress. Thus, we can see that the maximum shear stress that this beam will sustain is at the support reactions 7.8 and minus 6.2 kilonewtons respectively. Similarly, it also gives us the points of maximum bending. In the bending moment diagram, here we can see that the maximum bending occurs at 10 kilonewton load value. This means that at this section the beam will experience maximum bending. This gives us an idea of what kind of material can be used in which section of the beam and if there is any necessity of adding reinforcements in any of this section. Our previous example was a simply supported beam. Now, our previous example was a simply supported beam. Let us take the example of a cantilever beam this time. A cantilever beam is fixed on one end and free on the other, as we saw earlier. Since this end is a fixed end, we have three reactionary forces, and those reactionary forces would be RH, which is the horizontal reactionary force, RV, which is the vertical reactionary force, and a moment, which is M. This is because in a fixed end, the beam is restricted from motion in both horizontal and vertical directions as well as rotation. Thus, we have these three reactionary forces similar to our simply supported beam. We will have the same span and distance of both loads, the concentrated point load acting at 10 kilonewton at a distance of 3 meters from the fixed end and the 1 kilonewton load that acts on a 4 meter span from the free end. Our next step is to calculate the reactions and moments in this beam. We know that the net force within the beam is equal to 0 and RV, which is the upward load, should be equal to the net downward load. And this is equal to 10 kilonewton plus 4 kilonewton. So, RV here is equal to 10 plus 4 kilonewton. Again, this 4 kilonewton is the result of 1 kilonewton per meter load that acts over 4 meters. So, which is 1 into 4. That way we got RV equal to 14. Let us start with the RV or the fixed end. We have a maximum shear force of 14 kilonewton, which is positive 14 kilonewton, and we can say that it's acting upwards. Thus, we have 14 kilonewtons here, and since there is no change, the shear force remains constant until there is a negative 10 kilonewton force. Thus, the next shear force at this point, which is AW1, is equal to 14 minus 10, which is equal to 4. Again, shear force remains constant as long as there is no change in the load. As soon as we start the uniformly distributed load section, the shear force reduces at an intensity of 1 kilonewton meter for a span of 4 meters. Thus, the net reduction in shear force from W2 to R2, which is to the end of the beam, is equal to 0. That is 4 minus 4 into 1 kilonewton. The next shear force at the free end is equal to 0. We already know that cantilever beam is fixed on one end. The fixed end prevents any rotation in the beam. Thus, there is a bending moment component that occurs at the fixed end. If we are to calculate this bending moment, this would equal to the moments exerted by all the forces on the right side of the beam. Bending moment units are in kilonewton meter in this figure. Since we know that there is a bending moment component at the fixed end, we can start calculating the bending moment from the free end. We know that bending moment at the free end will be equal to 0 as there is no reactionary components beyond this point. Our next step is to calculate the bending moment at W2. This is done by resolving the uniformly distributed load into a point load as 1 kilonewton. 1 kilonewton per meter multiplied by 4 meters, which gives us a point load of 4 kilonewtons. This 4 kilonewton load acts at the center of gravity of this load system, which is at 2 meters. Thus, we can calculate MW2 to be equal to minus 1 into 4 which is 4 kilonewton load acting at a distance of 2 meters. Thus, the moment at W2 is equal to minus 8 kilonewton meter. However, as this is a uniformly distributed load, the shape of the curve will be a parabola. Our next step is to calculate the moment at W2. This is equal to minus 1. Our next step is to calculate the moment at W1. This is equal to minus 1 into 4 into 5. Here 4 is the resolved or uniformly distributed load multiplied by 5, which is the distance from the section, that is equal to 3 meters plus 2 meters, or the distance at which the uniformly distributed load will be resolved into. This is equal to minus 20 kilonewton meter. Similarly, the moment at the reactionary forces, which is basically at the fixed point, is equal to minus 10 into 3, which is the distance at which the 10 kilonewton load will act, minus 1 into 4 into 8. So MRV is equal to minus 62. So it's basically minus 62 kilonewton meter. This bending moment is due to downward acting forces. Thus, the entire bending moment values are negative values. For differentiation, we have depicted this in orange color. If we now combine the shear force and bending moment diagrams for the cantilever beam, we can plot the shear force and bending moment, and we can say that shear force is completely positive within the given region, and also bending moment is completely negative within the given region. And we have to take note that shear force is depicted in kilonewton while bending moment is depicted in kilonewton meter.